we're looking at less than 5.4. We're going to be analyzing binomial random variables. We're going to calculate and interpret the mean and standard deviation. We're going to find some probabilities. We're going to look at some cumulative binomial probabilities as well. So first thing we're going to do is figure out how to calculate the mean. Quite easy it is, quite easy. We just do n, our number of trials, times p, the probability of success for each trial. Oh, 49. I'm probably too soon to drink the Red Bull. But it's got to last me, like, I need that energy kick to last me till 5. I just brought one. And I don't want to go buy one. I just bought a case of them at Costco last night. So well, it's time to really, you know. You do? Dang.
Oh, like, you get Red Bulls and
Monsters?
and they're monsters, and then it's all on the basis of our
Rockstar?
weird. But it's like, it doesn't work as good as a monster.
Okay. You'll just take a nap? Nice. Nap is not in my future. I guess it could be, but I have a little bit of work to do. I would feel kind of bad having napped and not done work. And then I wake up from my nap and I'm like, whoops, still have that work to do. All right, so that's the formula for that. Also, we're going to calculate the standard deviation. It's going to be n times p, right? My number of trials times my probability of success for each trial. Right, the square root of all that, right? 1 minus p and all that. We'll apply this formula quite shortly here. Just another short formula we need. And as the book is saying, you know, that is only going to work for a binomial situation. I just decided to go for it. Mm. Yeah. Yes. Yeah, that hit just right. Other adults are perplexed by me, but I speak a little bit like a teenager, but I'm a grown man. Whoops, almost. Okay. So let's look at an example. Right, we've looked at the type O blood example quite a bit, right? So we've got the groundwork laid for this thing. Now we can find the mean of the distribution, right? The mean is the number of trials. It says 5, so that's where this one is coming from. Oh, I just don't like that. So this one, right, is your number of trials. And then where does the 0.25 come from? Right there. Basically, in all of these problems, there's two numbers. One's a probability and one's your number of trials, right? The probability is the one that's a decimal. No problem, huh? Is everybody drawing right now? Oh, no, sorry. You guys are both drawing. It's okay. I get it. It's okay. No, no. I'm not saying I have a problem with that. I was just noticing. It made me kind of want to be artistic. Okay. If we're going to calculate the standard deviation, we would do it like this. No problem. That's not what NP stands for, though. No problem. So. I'm so glad that this mask just like barely touches my face. I know that kid. I was almost going to be an earthbender today. I decided not to do it. It's just too much work. I didn't have a chance to go like buy all the stuff for it. I have stuff for everything else, but I couldn't figure out this date. Huh? Is it a fire then? That's pretty cool. That's pretty good. All right. Okay. So we can also calculate some probabilities as well with this, right? So before we would calculate the probability of exactly one value occurring, we can change it up and we can do the probability of more than one, right? So probability x is less than or equal to 1. Now, because we have these all worked out for us, it's easy just to add them, right? But what if we weren't? What if we didn't have any of this stuff, right? I'd have to calculate the probability x equals 0. Then I'd have to calculate the probability x equals 1. And then add them up. And I'm going to show you there's a faster way to do it. And I think I'm presenting this in the wrong way if I want to show you my calculator. So I'm going to change that real quick. All right, so let's see here. Where's my calculator? Did I put? Oh, there it is. All right. So we're gonna go second bars. We're going to the same place that we went for the binomial PDF, and now instead of PDF, we're going to choose binom CDF. It's going to add all that stuff up for me. Just remember that it's only going to do things less than. Okay, so we're going to have to figure out a situation with how to deal with it with greater than. So our number of trials in this particular case was, how many was it? It was 5? Yes, there were 5 trials. Each had a probability of 0.25. So 5 with a probability of 0.25. And we want to know the probability that x is less than or equal to 1. Okay? Less than or equal to 1. We're going to hit constant. And we get a probability of 0.632, which is awesome, right? It matches all this, and they had to do a bunch of extra work. We do not. Right? Matching that guy without the extra work. Okay, now what if you want to do the probability that x is greater than 2? Well, you could add up all that stuff, right? Which would take a little bit of work, right? Or we could use our calculator, but the caveat is that before we use the calculator, we got to realize that the calculator only calculates probabilities less than, right? But what we're looking for is the probability that it is greater than or equal to 2. So we're looking at, we would have to add all this stuff up, right? So what we can do, if we're going to use the calculator, is instead find the probability that x is less than or equal to 1 and subtract from 1. So what I'm saying is that the probability that x is greater than or equal to 2 is the same thing as 1 minus the probability that x is less than or equal to 1. So then you'd be able to do that with your calculator, right? You do the binomial CDF with trials equal to 5, probability equal to 0.2, and x equal to 1, and then you would subtract that from 1, right? You know what I'm saying? Like, so the probability that x is greater than or equal to 1, right? That's, right, we figure out this probability, and then if we subtract from 1, we get this stuff, right? Because these have to add up to 1. All these probabilities have to add up to 1. I'll leave that there for fastidious note takers. It's a sick name for a band. I was in a band for a lot of years, and we had to change our name at one point. And our drummer was stuck on Nefarious Wheel Bite. I said, "No, dude, that's a crappy band name. It's cool, but it's a crappy band name. You only understand what it is if you're a skateboarder and you know what the word nefarious means." All right. Let's do an example. A local fast food restaurant is running a draw 3 get 1 free lunch promotion after each customer orders. A touchscreen display shows the message, "Press here to win a free lunch." A computer program then simulates one card being drawn at random from a standard deck of playing cards. If the chosen card is a 3, the customer's order is free. The probability of drawing a 3 is 4 out of 52, which actually turns out to be 0.077 if we put that in our calculator. Otherwise, the customer has to pay the bill. Suppose that 250 customers place lunch orders on the first day of the promotion, which means that, what this means is that n, my number of trials, is 250. We'll let x equal the number of people who win a free lunch. Okay. So, 1, explain why x is a binomial random variable. Well, so for number 1, what do we got to do? We got to check games. So, either you win or you don't, right? Each trial is either a 3 or not. So that's binary. One customer winning doesn't affect the probability of the other customer, right? So they are independent. Winning. Whatever happened to Charlie Sheen? Maybe we're all glad to have forgotten that even happened. All right, N, there are a fixed number of trials, right? And then S, the probability of success is the same for each trial. And there you go. Number one is done. We checked bins, and each one of these elements of bins is satisfied. So then we can say that we have verified that X is a binomial random variable. Let's find the mean of X. Oops. 2. Easiest question. Right, 250 trials, the probability of success, 0.077. 19.25. We got to interpret this in context, though. So, in 250 trials, we expect there to be around 20 winners. Number 3 is asking us to calculate and interpret the standard deviation. Sigma sub x is equal to, where it's n times p square root. Ooh. Square root of n times p times 1 minus p, which is the square root of, we'll just put 250 times 0.77 times 1 minus, oops, 0.077, 0.077. Right, that's 19.25 times 0.923. Let's calculate that thing, the square root of 19.25 times 0.923 is approximately 4.215. So the number of winners should vary on average by 4.215 winners. That's how we interpret that. $4.215 winners on a share. All right. goodness. Huh? I don't know what happened here. All right. All right, number 4. Says that one of the customers is surprised when only 10 people win a free lunch. Should the customer be surprised? Find the probability that 10 or fewer people win a free lunch by chance alone, and use this result to support your answer. So, we got to just find the probability then that x is less than or equal to 10, right? And this is where it's going to be really awesome to have this calculator function, because wouldn't it suck to have to go 0, right? Calculate the probability for 0, then calculate the probability for 1, then for 2, then for 3, then for all the way up to 10 and add them all together, right? It would take a bit of time. Instead, we can just put this into our handy-dandy calculator. Remember, it's second bars. We go to Binomial CDF. Our number of trials was 250. Probability of success for one trial, 0.77. And we're going to see the probability of 10 or less. That is going to be 0.013. That's very, very small. Around a 1% chance that you get out of 250 people that play this game that you get 10 or less that win. And you can imagine, right, as this number gets bigger, right, if you were to calculate 20 or 30, this probability is going to get really small too, right? It's going to get really, really small for the bigger, because, you would expect that if there's a really small chance of winning one time, right, that around 8% chance of winning, that the chance of winning a bunch of times is going to be small as well, right? And we can even look at it, right? You'll see, like, the probability that x is 1 is probably, or even 2 or less, is probably pretty high. So we could look at that. What about if this was 2 instead? Oh, it's really small. Okay. Let's go to 5 winners. Still quite small. 5 or less? Let's see. What about 20 winners? Should be quite small as well. Or at least 20 winners? Oh, that x is 20 or less, sorry. So 1 winner counts, 2 winners count, 3 winners count, and so on, right? So that it makes sense. Right, not all of them, not exactly 20, but there are 20 or less. All right. Awesome. So we did these things. It was awesome. And that's all I have to say about that.